Everybody, welcome to the webinar. I just wanted to plug that if you're a new user, this is a perfect application training webinar for you to get started on Celigo, or a refresher for what's important on acquiring bright field images on Celigo. So that's kind of the first part of what we're going to cover. Then we're going to talk to you about how to set up segmentation parameters and what's the important point of the parameters and the images that work together with algorithms. After we've got the image algorithms analyzing the data, we're going to show you how to review your images and export data and save images. And then we're going to save the experiment so we can reproduce the same process for the next data point on the scanning for our proliferation curve. So we'll load the plate with that saved experiment, and then we're going to produce growth curves showcasing how when you have imaged multiple times on a plate, how to produce a growth curve. But mostly I really want to focus some extra detail on the first 2 points, how to acquire bright field images and set up segmentation parameters. So let's get started. So on your screen, you're going to select the icon Celigo to start the software. The system will go through some startup procedure and then give you the Start tab page. At this point, you'll notice the dialog box up at the top. This is a workflow tab, so you can basically tell where you are in the workflow of the whole process. When it's brown, that's where you're actively located. And the first thing you have to do on the Start tab is to log in as a user. So in this case today, we're going to log in as demo with no password. Clicking in Login will give us 4 options now. We can either create a new scan, view and analyze scans, do batch analysis, or batch export. So for today's training, we're going to cover the first 2 buttons. We're going to create a new scan so we can have images of our proliferation and bright field. So the first thing we'll need to do on this section is select the plate type that we're going to be imaging. You can see all the different formats that the Celigo can image. Today we're going to use the 96 well plate. And then we need to provide the manufacturer of the plate and the catalog number. This is going to be the 655090 plate. Then we'll give our plate ID a unique name, and all the scan times will be on this one plate ID. And then we'll click Load Plate. From here, the stage will move open, and you can put your plate on the stage, and then click OK. If you're facing the instrument, A1 is in the upper left-hand corner. The stage will move back in, and the system will migrate the workflow over to the Scan tab. So down on the Scan tab, you can see where the brown button has gone from the start to the scan. Now the first thing we need to do on this tab is select the application. On the drop-down menu, there's a lot of different options. For today, we're going to do the first one, which is Confluence, and it's just a bright field single channel application. Once you select it, the parameters will update, and on the left-hand column, you'll see what I call the setup parameter area for scanning and acquisitions. This section here, the large rectangle, is the image display area. And then this is the plate map navigation and selection area. And the little map on the bottom is your well map navigation area if you want to look at different areas of the well in a plate. So first we'll want to acquire good bright field images, and I'm going to show you how. First we'll turn on the live camera. These are the camera controls up here. Just click on live and it turns to a light blue. That means it's active. Now we're going to navigate the stage to move over to a well for us to set up the focus and illumination. So I usually like around C3, C4. We'll choose C4 today. The system will move there, and you can see this is the live image. It's a little out of focus and dark, so we'll want to, you can pan and scroll with your mouse to zoom in. The first thing we'll want to do is set up the illumination settings in this portion of the screen here. And the auto exposure and gain is automatically selected for bright field illumination. The only thing you need to do is click Apply. I'll explain what's going on here with the images when I say auto exposure and gain. So you'll see that the text box down here, it says intensity at 90. That's the current background of the grayscale that you see. The camera range is from 0 to 255. We want to be in the middle of that range for bright field images. So when you click apply, the system will figure out what exposure it should have to return a background image that's in this range. And you can see the value is now updated to like 125, 130. So now all the images will have that grayscale background. Next, we'll want to set the system to focus. But before we do that, I want to kind of explain a couple of different options for focusing. The first one is image-based focus. So if you have a lot of content in every well, image-based focus might be your first option. And I'll explain what happens. The system will study the stage, figure out what is the best focus. Very similar to what you would be doing on a microscope. That is what it's studying to figure what should be in focus. And then when you navigate to the next well, the system will try and figure out what the best focus for that well. This works when you have content in every well. But if you're doing something like proliferation curves or cell line development with very few cells in a well, this might not work because you don't have enough content in the center of the well. So what do? So then you would select hardware autofocus. How does that work? So the system, you'll basically want to pick a registration well that has a lot of content in it. And here is an example of 3 wells, one with a lot of content and the others with maybe 1 or 2 cells in it. And their focus planes are in different areas. So when you click the focus setup and register the well, it studies the cells in the well and returns the right focus. Then it places 2 LED beams on the bottom of the plate, and it measures the reflected spots in the distance between them. So this measurement, it knows it has to be at this distance apart from each other for the cells to be in focus. So when it moves to the next well, he sees the beams are too far apart and will then move the stage up or down to appropriately have the beams the right distance apart, knowing the cells will be in focus. And the same if the cells or if the wells are too high, it'll move down because it knows the beams are too close together. So this is how the hardware autofocus mechanism correctly picks the right focal plane at the bottom. Let's see how it works in action. So we click Focus Setup. The dialog box opens up. And the default is actually set up for hardware autofocus because that's what we prefer or recommend. Then you just click Register Auto. You'll see in the image display area, the cells are actually going to move in and out of focus. This is like what you would see on a microscope. The system is actually trying to figure out what is the best focal plane that has the best contrast of the cells. When the system has found it, it'll stop there and the hardware focus beams will be registered on the bottom of the plate. You can tell when this dialog box changes to say the word registration at C4 that the system has been registered. Now you can close the dialog box. So let's zoom in a little bit and check out these cells. Just use your mouse to scroll in. And I just want you to observe some of the morphology of the cell. You can actually see there's a lot of detail in the cell itself. You can almost see the nuclei and some little dendrites or cell navigation podites. So this is a little bit too much detail for the image algorithm. Now, for those that have never done image analysis before, I'm going to give you a little education on what an algorithm is. So let's show on the next slide the different image analysis algorithms that are on Celigo. So the first one is called bright field algorithm, and it's looking for objects with a bright center and dark edges. So here's an example of a long adherent cells. If you draw a line over the cell and plot the pixels of that line from the image, you can remember that the camera pixel intensity range is from 0, which is black and white, to 255. You can see this kind of profile for that line over the cell. Then we have a value or a threshold that we cut off anything below or above that line, and then we draw a green graphic overlay around the cell that has object pixels above that threshold. And it would return something like this on the screen in the graphic overlay. Now the fluorescent algorithm for the fluorescent images does something slightly similar but slightly different. It's got a lower background close to 0. So it's also looking for bright pixels, but the delta between the background and the signal of the object is much bigger. So if you drew a line over this fluorescent cell, the profile of those pixels would look something like this, and you can see that the background is much lower on this camera scale. And the graphic overlay was purple would be outlined like this. Now for dark objects, the algorithm is looking for cells with no bright center, but below the background level. So it would return something similar to these, this cell. And then the fourth algorithm is the texture algorithm. This is typically used for large objects or confluence areas, which is the application that we'll use today. It's looking for a lot of pixel changes in a localized area beyond the cell size, so beyond like maybe 50 or 100 microns. It's going to look for a lot of texture pixel changes. Those are the four algorithms that the Celigo uses to detect objects in the image. So this is a little bit of foundation. You can carry this into any application that's on the Celigo. So let's come back to our image, and you can see now the cell that we're looking at has a high contrast with a lot of detail inside the cells. So how do we actually get less detail to properly detect these cells? What we'll need to do is actually create a slight blur in this image. So we need to defocus the image. And how do we do that? With the live camera on, we'll just click on the down arrows here. And our current registration position is here, 4.672, and we need to determine what the focus offset should be from the hardware focus registration. So if you just click once, the stage will move 1 micron down. So clicking each time is another micron. As we do that, you can see the image of the cells start to get a little bit blurry in the body of the cell, but it's clear that you can see a darker outline on the cell body. So this is going to help us. So this is the ideal focus. You want a very bright center with dark edges, and defocusing can help you acquire this focus image. So this is negative 14 microns from the registration, hardware focus registration. So by clicking set offset, the button to the right, you're basically telling the system to register the hardware focus beams, or run the hardware focus beams on the bottom plate, move to the right focal plane, and then move 14 microns negative from those beams to collect this properly focused cell. Okay, next we'll want to select the wells on the plate for imaging. And we're not going to do the whole plate, we're just going to do this small subset in here. So that requires you to click the selection button and then just highlight the wells. Now we'll click Start Scan. So the system moves us right over to the Analyze tab. And you'll note down below on the left, there's a scan progress bar that's lit up with green. So that's the current progress for the image acquisition of the cells that you've selected to be acquired. When this image is acquired, it's automatically saved to the hard drive, and the wells on this plate map will turn green when it's been saved. So you can see the first well has been saved and turned green. If you want to start viewing them, you just double click on those green wells, and the images will be displayed in the viewing area. So let's click on B5. And you can see the whole well is now displayed. Just turn on the graphic overlay for the confluence and the well mask. So the analysis parameters are automatically displayed on the left-hand side, and the default settings are pretty close to what you'll want to start with. We'll go over those in a minute. But you can use your left mouse button to move the image around and then scroll in on the image to kind of zoom in and see what's being picked up and what's being ignored. So it's doing a pretty good job. What I probably would recommend is maybe moving the well mask in a little bit. So it's just a little bit outside the well wall. And you can see when you click Analyze, the graphic overlay adjustment you just made will update on the image itself. So maybe just a little bit outside that. So let's do 99.2. and then click Analyze, and the graphic overlay will update. If you don't want to keep clicking Analyze, you can also just checkbox Auto Analyze, and it'll automatically update when you change a number in that column. All right, so let's select another well with a little bit more content that's probably more challenging for this algorithm. All right, so B10 has a few more cells in it. And let's zoom in. And at this point, you can see that it's got a lot more cells. And I just want to remind you how the algorithm works. So we've got 4 different algorithms. Because we chose Confluence as our application, the default algorithm is the texture one on the bottom here. And it's looking for a lot of pixel changes in a localized area. So it knows it's the background, if it's flat, it's going to be ignored. If there's a lot of pixel changes, it'll be outlined in green. Okay, here we are in our sample. With the default setting threshold at 15, it's doing a pretty good job, but it's got some vacant areas. Let's increase the threshold to 18, click Analyze, and see it should pick up less content. There, it did a better job. So you can see increasing the threshold is picking up less texture changes or stuff that requires more texture change. Okay, I'm happy with that. So let's click Selection and highlight the wells, and then click Analysis Settings and highlight the wells with on the plate map, and then click Start Analysis. So now the system will move automatically over to the Results tab. The plate's done imaging, and it's going to continue to analyze this data set with the parameters that we just described on the Analyze tab. At this point, we're looking at thumbnail images and the confluence percentage area of that well. While the system is analyzing, I like to actually add some information on the description tabs. So there's 3 tabs. One is the plate itself, so you can provide content of the content in your plate. And then the scan would be the image time right now, and the scan result would be the analysis result, such as confluence is what we're doing today. So if you have details you want to put in there, like what were the settings or something, you can put that kind of content in there. Okay, so our system has finished analyzing all the images for this scan, and you can see the data is displayed over the thumbnail. So we go from 6% all the way up to about 40%. You can also use this other icon called the Fill icon button. What it does is it fills in the areas it has called out as confluent. So it gives you kind of a high-level view for the area of detection. Right now I don't have a ton of cells in these wells, but you can see on the right side, 40%, it's about right. That looks good. So to turn this back to the data display, you can either click Fill again or the image. And here are the values again. Double-clicking on a well will, in the image display area, you will provide you the high-resolution image. So let's double-click C10. And then you can again scroll in with your mouse, or even double-click will jump right away to a very zoomed-in level. And then the graphic overlay appears when we get to the high-resolution image. Now I'm just looking to see if the graphic overlay has properly detected the cells according to our analysis parameters. And clicking on the fill icon here will fill in the areas that it's calling confluent. So now it's a little bit easier to see how the outline works, what's in and what's out. And then you can click through to different wells. Basically, if you click on the plate map, it will stay at the zoomed in level and in the location in the well, but if you just click on another well, it navigates to the next well over. Now let's go back to the scan or the plate level view by clicking back to scan. And now I want to show you how to save this whole process so we can use it for the next couple of scans that happen for our proliferation curve. So click on this little icon here, it's called experiment, and give it a name. And then I will give something probably unique to this process. So we're doing confluence at Brightfield and a 96 well. All right. Now I want to show you how to capture some images maybe for your report if you want to do some image grab for your reports. So there's two ways you can save images for reporting processes. This display area is a rectangle that's currently displaying the green graphic overlay with the fill icon on. You can actually do this as a screen grab. You can turn on and off any one of these parameters up in the graphic overlay for your desired look. And then if you click up here on this icon that says displayed image, you can save this square rectangle as is in any one of these three formats, JPEG, TIFF, or bitmap. So let's just call this displayed image with graphic overlay. So you can understand there's two different ways you can save images. This one has the graphic overlay at this zoomed in location at this level, or you can export the raw image, which is the whole well at the high resolution level. So export images. So the image will be stitched together, so the whole well will be together as one, and you can save it at any format you like. Let's do JPEG. And then you can save it to any folder location. At this point, we'll just put it on the desktop. And then OK. And let's review what does that actually give you. So here on the desktop, let's see, I've got my display image with graphic overlay, and it's a rectangle. Here's what it looks like, exactly what we saw on Celigo. So the only way to get your graphic overlay to show up is this way with a saved image, unless you have a third-party software that allows you to capture screen grabs. This is the raw image that's taken from Celigo. It's the whole well. It's the highest resolution. You can zoom in and you can see your cells on a very cellular detail. So this is a little bit bigger in size, but it's the real raw image quality picture. The whole well. So those are the two different ways you can save the Celigo images yourself, unless you have third-party software that allows you to do some kind of screen clipping on your own. Okay, so let's go back to our Celigo. Here we are. Let's go back to the scan to return to the plate view. It's this little brown button. Okay, let's end this current session with this little blue box. I don't want to close the software, I just want to end this session that I'm currently imaging. By clicking on this little blue X or white X, it gives me back to the Start tab, and then I can use this eject button to remove the plate from the stage and put it back in the incubator. So if you're doing growth curves, you probably want to incubate it over the next 24 hours, and then you're going to want to image the plate again. So here, let's just take the stage or plate off the stage, and then the system will go back. And on the next day, we're going to load the plate again with that saved experiment. Okay, how do we do that? Well, first we'll create a new scan. And we're going to do the same thing that we did. We are going to select the plate type, which is a 96 well plate, and the plate manufacturer and catalog number. This list is alphabetical, just to let you know. Griner is in the middle. And then the plate ID, we want to grab the same one that we imaged from the day before. So that's this scan plate ID name here. Or if you had other plates you wanted to use the same experiment, you can do that too. Here's the unique part. We're going to select from this area the experiment name that we gave. So in the drop-down menu, you'll see Confluence, Brightfield, 96 well. So this remembers everything such as the application, the focus, the illumination, the analysis settings. It asks, do you want to perform autofocus registration? We'll click yes. This means when you put the plate in, it will go to C4 and do the auto registration for focusing. So we put the plate on the stage and then we click yes, the stage goes into C4 and it begins to study and apply the hardware focus registration to C4. When it's finished, it will take us to the scan tab. And now you can see here the system has remembered from that saved experiment that we're in the same Confluence application, and it's remembered all the focus and illumination settings that we described in that first scan. You don't have to change anything, but if you wanted to, you could. But the whole point is you want to have it remember everything. And then here you can observe that it did a good job with the focusing and the focus offset. We have that white center with the dark edges on the image in C4. So at this point, we just click Start Scan. Now the system moves over to the Analyze tab and starts to acquire the images. It has remembered the saved analysis settings that we have basically selected and the same wells. We just click Start Analysis. Again, you can make changes if you want to. All right, now we moved over to the Results tab. You can enter in information into the Description tab, but I want to point out at the bottom of the screen, you'll see two progress bars, Scan and Analyze. It's like happening at the same time. So as the images are acquired and saved on the hard drive, they are also being analyzed with the analysis parameters. So that's what's being populated on the plate level view, the thumbnail image, and the data for the Confluence measurements. So I use this time to actually write into the description some additional detail. Okay, so now we have finished the second scan for the same plate, and you can see the values have come out very similar, 6% all the way up to 40% Confluence. Obviously, it's a cell titration. And then you can use the fill icon to verify the Confluence measurements are looking good. And clicking back to image, we'll switch it back to the data display. You can, at this time, since it's finished analyzing, click between the scan times. Just use this toggle bar to find the scan time that you want to look at. So we can look at the two different ones that we did. And the thumbnails and data will update according to this first scan. And it looks very similar. Now at this point, you'll notice that the progress bar, we have some white text on Scan and Analyze. That means you can actually navigate back to the Scan or Analyze tab and do an additional scan, and you can make updated changes or reanalyze this image set if you want to. Let's export this scan time into a CSV file format that we can go observe in Excel. So let's give it a file name. And then you can see this one will say scan 2 because it's the second scan that we did today. And then let's go to the previous one by changing this toggle bar up here. And then click Export Well Level Data. So this is just 2 data points. It's not a big deal for exporting in this fashion. But remember on the Start tab, there were 4 buttons. There was 2 additional ones we're not going to cover today, but that would be if you had like 10 scans and you wanted to export 10 of the data 10 days, you could do batch export that way. All right, so let's review what does the CSV file format look like for individual days being exported for Confluence. So here are 2 CSV files. We'll open up in Excel. At the top portion of the scan, you'll see a lot of plate detail information. So you have the plate ID, any descriptions you put in there, the plate type, the time, the user. The next section down is your measurement that you chose for your application. So this was the Confluence measurement, and the data matches with what you saw on the screen. Okay. So let's go back to the Celigo software. And I want to show you how to make growth curves. So you'll need at least 3 to produce a growth curve, 3 scans. But if you have 4 or more, you can get a 4-parameter fit. So I'm going to use one of the demo scans that are provided on the instrument to showcase that. So let's click Cell Counting, Confluence, Adherent Cells. This plate was imaged over 12 days, every day. And you can see that in the description tab, I've provided the day value. But you can see it's dated on the scan time, all under the same plate ID. So if you can at this point click on any of the time point scans, and then the next grouping down is the analysis that was done on this scan time. So currently there's only one analysis done on this scan time, it's Confluence. Again, you can reanalyze as many times as you want and it'll just list them all right there. And then you load scan and it'll take us right over to the results tab in the plate level view. At this point, you can see the percentage displayed on the thumbnail images, but I also like to use the fill icon to kind of see high level what kind of confluence area was detected. The green is what was covered, or what the system calls cell coverage. And at this point, you can also toggle in time. So if you didn't pick the right time in the scan or start tab, then you can also navigate to different times here in this toggle menu. Okay. So later time points, obviously I hit 100% confluence on day 8. So maybe let's just look at the first 7 days for making growth curves. I don't think we need to use 12 days of 100%. So let's double click the high resolution, to observe the high resolution image. And you scroll in or double click to get the zoomed in level. And you can see this is day 2, so the day after plating. You have some cells sitting here. There's a cluster 2 right there. It's probably divided from yesterday 1 cell. So I'm at a certain zoomed in level, and if you click on the graphic overlay for confluence and fill, you can confirm, yes, those were detected. But what's cool about the software here is on this plate map, you can toggle in time to observe the cells growing individually. So we just saw 2, now it's a lot more and a lot more. So this is really neat if you're looking at cell line development to observe a single cell grow into a multiple cell colony. Or if you're finding a well that has a colony and you want to observe, was it a single cell or 2 cells on day 0, you can also do it that way. And here's the confluence fill view. So this is a really neat application. Like I said, if you're doing cell line development, you do serial diluting of your cells, you got a single cell in a well, it grew into a colony. So you would first identify the colony and then go back in time to see it was a single cell. Now let's go back to the scan tab and I'll show you the growth curves for these 12, well, we'll do 7 days. So clicking on the reports button takes us to a new page. Here are all the scans, and the slightly tabbed in section is the results for that scan time. So we'll just check the first, I think maybe 7 scan time results. So just checking the box is selecting it for putting it in the graph. And then in the upper right corner, it says object level data, selected report. We're going to change that from that to Confluence, growth tracking Confluence. That's the kind of report we want to show. Click generate and it puts the data set into a graphic form like this. So each well is plotted according to its data set from the times that we selected. You can look at a normalized growth chart or just a regular growth chart. They're also presenting doubling time and doubling rate as other ways of data display. So when you click on a well, the graph shows up on the left lower corner for that specific well. And you can export this file or this growth curve, which has doubling times and rates, into a CSV file as well. So we'll call this Confluence Growth Tracking Data. So it would basically provide you on a well-by-well basis the growth data. So let's go and view this Excel file. Okay, so those are the individual CSV files. Here, as we open up the growth tracking data, you'll see the top portion again is plate level information. The next section down is doubling time in hours, and then we have doubling rate. And then each well is represented here. You can see this first one is B3, and the columns that are provided is the date and time, the elapsed time, the percent confluence area, the well sampled, which means we did a whole well, and then the doubling point in hours. And then down below is the 4-parameter fit curve values. Okay, so we've covered a lot in today's training session, but it's a very good getting started point on how to acquire good bright field images on Celigo. And I really focused on the hardware focus and image-based focus mechanisms. People ask a lot about what's the difference. And then I also showed you how the algorithms actually pick up objects in the image and how it's being analyzed in the system. I showed you a lot of ways to review and observe your data and exporting images and CSV files. I showed you how to save an experiment, which is the whole process, and then load that experiment so you can do easy proliferation acquisitions, and then how to produce growth curves after you've got so many days of imaging. So that's a lot, and I would like to open up the forum for questions if anybody has any.
Great job, Sarah. I think that was a really great presentation. Alrighty, so like Sarah said, we are opening this time for any questions our attendees have for us today. So I'll just give you guys a minute or two to type those in. And while we're waiting, I would just like to remind our attendees that we really do encourage you guys to submit topic ideas for us. So if there's a specific cell type you're interested in seeing on the Celigo, a specific application you're interested in seeing on the Celigo, or even one of our ceilometer instruments, it doesn't matter. We'd love to hear your suggestions for future topics for webinars. You can email them to us and give us a call. There's a short survey you can take at the end of this webinar. You can type in your recommendations there as well. So I'll just give you guys a couple more seconds to see if we get any questions that come through for us. Alrighty, so I'm not really seeing any questions come through. Oh, I see one that just popped up actually. Let's see what this one says. Okay, first question. So does setting focus offset increase time of image acquisition per well?
No, not really at all. You won't even notice it. The system is really fast. The LED beam itself is super fast, and then the stage movement in Z is super fast. You wouldn't even notice it. Just to point out, if you do fluorescent imaging, you may turn up your exposure time. That's where you end up losing or slowing down the system if you have super high exposure. So I cover that kind of content in like a viability assay webinar.
Alrighty. Any other questions for us today? Feel free to type them into the questions bar.
I do want to make a comment. So I basically talked about a lot of different algorithms, bright field counting, fluorescence, dark field, and texture. Today we covered the texture algorithm, but the way I was teaching you how to acquire the images with the focus, I keep doing that, it allows you to count the cells in early time points if you wanted to do cell counting. But I showed you that algorithm confluence texture works on those bright field images. So you could analyze it in either way, direct cell counting or confluence. I find that the confluence works easier when the cells are really overgrown in almost 100%.
Alrighty. We do have another question that came through. Is there more accuracy with a certain algorithm over others? Is bright field better than texture, or is it based on cell density?
So we've done parallel studies where we basically analyze the same images in confluence and direct cell counting, and it paralleled very well. I feel the challenge you have with direct cell counting is when your cells are so flat that the bright field algorithm will struggle with very flat cells. Like MCF7s, they tend to form colonies and are very flat cells. So I would prefer to use confluence over direct cell counting. So again, it's cell type specific. Direct cell counting is super easy for suspension cells. I've also had good success with A549s on direct cell counting. But if you find that that's challenging and not quite working out for you, you can reanalyze in confluence and the data will look just fine. It'll look good.
Great. Thanks, Sarah. Any other questions for us today? I'll give you guys just another couple seconds to see if we get any last minute questions typed in for us.
Can I point in another comment or my own personal? If you're curious to know how many cells are actually in the well and you really can't get a good count from direct cell counting, you could do a nuclear stain like Hooks at the end and do a fluorescent image acquisition to get the counts and parallel that with your endpoint confluence measurements if you really wanted to know how many cells were in that well with that confluence measurement. That's something you can test drive on your own.
Great. I think there have been some really good questions and comments and discussion for this webinar. I'm not really seeing any more questions come through, so I guess this will conclude our webinar for today. I'd like to thank all of our attendees for joining us today for the Celigo user training webinar, and I hope you guys join us again next month. Again, today the session was recorded, so you will be able to watch it again if you wish to do so, or you can even pass the recording along to a friend or colleague if you want to share the content with them. That's perfectly fine. You will receive an email either today or tomorrow with that link to that recording. Again, thanks everyone for joining us today. And Sarah, I think you did a really great job presenting, and I hope everyone has a great day.
Thanks, Amy. Thanks everyone for coming.
Goodbye.